Ladies and gentlemen, my name is Andy Zoidman and welcome to my talk Massively Parallel, Highly Efficient, but What About the Test Suite Quality? Applying mutation testing to GPU programs. Let me first state that this work was led by my brilliant PhD student Chin Zhu, and with Chin having left academia and ICST being held later in the year, it's up to me to talk about her brilliant work in this video. Let's focus first on the exact situation that we're in and what is the difference between a central processing unit and a graphical processing unit, a GPU. A CPU, which we use for traditional programs, consists of a few cores. Typically you have 4, 8, maybe 16 cores in a regular notebook, computer, or mobile phone. Yet in a GPU, we have thousands of cores, meaning that a lot of work can be done in parallel. GPU programming is about exploiting these many cores for very intense computations. Now, GPU programming is not a completely different programming model. It is actually a programming model that is interleaved in the regular traditional code. And for example, NVIDIA's CUDA programming model works on top of, for example, C, C++, and Python. We're today focusing on C programs that are augmented with CUDA code. As the graphic shows, this GPU code often only consists of 5% or maybe less of the total code, but nevertheless, it is very important code, also if you look at the application domains of GPU programming. That can be bioinformatics, computational chemistry, finance, structural mechanics, computer vision, machine learning, or maybe computational fluid dynamics. I think this list shows that GPU programming is used in many pieces of critical software, and that's also why testing the GPU programming should require additional attention. Now let's have a look at our GPU code. This looks a lot like traditional C code with some augmentations. For example, on line 10, 11, and 14, we're actually copying data from our traditional program to the specific GPU that we want to access. The question then is, where are the bugs? And that could be in the traditional base program code, and that could be C. It could also be in the GPU programming code. Now, what we already have are traditional mutation operators that work on languages like C, Java, and many others. But what we don't have, and what is the real contribution of this work, are the GPU-specific mutation operators. Now, if we want to create GPU mutation operators that are useful and that mimic actual programming errors in GPU code, we need to have a better understanding of what are typical CUDA programming bugs. We started our investigation by performing a wide search on Stack Overflow. We analyzed 150 posts in detail and came to the conclusion that 48 of these posts can be traced back to a CUDA programming specific bug. By analyzing these posts, we extracted 9 GPU-specific mutation operators. Now, before talking about these specific GPU mutation operators, let's have a closer look at what it takes to do things in parallel when using CUDA programming. For example, the first line on this slide actually calls the sum method. And it says that this sum method should work in 4096 blocks. Let's have a closer look at how we can actually do things in parallel if we're using the CUDA programming language. We're calling the function sum here, but we're specifying that it should happen according to 4096 blocks, and for each of these blocks, 256 threads should become available. So we're actually summing a lot of data and we're cutting the program into pieces so that it can be actually done in parallel. What actually happens is that within each block, different threads solve part of the puzzle, part of the summing operation, and all that information is then brought back together to the base program. From this analysis of Stack Overflow and the 9 GPU-specific mutation operators, we actually came to the conclusion that the two main categories where we can design mutation operators for, mimicking those actual bugs, are in terms of memory management and thread management. On the right-hand side, you will see the 9 mutation operators that we've designed and that we're using in our study. One example of such a mutation operator is the alloc swap, and that replaces the number of threads with the number of blocks in parallel processor allocations, and vice versa. So in this particular example, we went from 4096 blocks using 256 threads to 256 blocks using 4096 threads. All details on all mutation operators can be found in the paper. Now, our study revolves around 4 research questions. And the first one is, how frequently can GPU-specific mutation operators be applied, and how good is the existing test suite at killing them? The second question goes into how effective are conventional mutation operators in evaluating the test suite of a GPU program. The third question is, how effective are GPU-specific mutation operators in evaluating the test suite of GPU programs? Finally, the fourth research question dives into how do GPU-specific mutation operators compare with conventional mutation operators in terms of the improvement. Our experimental setup consists of 6 GPU benchmark projects from the CUDA SDK, all of which are widely used in the research domain, but perhaps not in the software testing domain. The total lines of code in terms of production code for these 6 programs together are 2,650 lines of code. On the other hand, the lines of test code comprise 1,394 lines of code. If we combine research question 1 and 2, and we answer how frequently can we apply these traditional mutation operators versus GPU-specific mutation operators, we need to look at 2 numbers, namely 1,039 traditional mutants that we could apply, and 1,027 GPU-specific mutants that we could apply. Now that we know how many times we can apply these mutants, let's have a look at the mutation score that follows from applying them. For the traditional C mutants, we have a mutation score of 86%, meaning that 86% of the mutants are killed by the existing test suites. For GPU-specific mutants, we see a mutation score of 80.3%. Now, very important to understand is whether there are interactions between the traditional mutation operators and the GPU-specific mutation operators. Let's say we would only use traditional mutation operators and we would try to aim for 100% mutation score. Would that help in also killing more GPU-specific mutants? Well, the answer is a bit mixed. If we reinforce the test suite, the existing test suite, with suggestions from surviving mutants from traditional mutation operators, we see that the mutation score for GPU-specific mutants also goes up. But there are some remaining GPU mutants that are not detected by the C-sufficient test suites, and the majority of those surviving mutants requires more delicate and complex test cases to observe differences. That is why we like to conclude that GPU-specific mutation operators have their worth. So the discussion that we would like to launch with this paper is that with the growing importance of GPU programming, we should increase our quality assurance efforts for these GPU programs. Even if these GPU programs only consist of 5% of the overall code. Mutation testing can play a role here with traditional mutation operators, for example, for the C programming language. But additional GPU-specific mutation operators are useful to cut out some very specific situations.